I now want to introduce to you this concept of balancing chemical equations. You see, before we can really use chemical equations, we have to balance them. We do this by adding coefficients in front of each formula in the equation until the total number for each atom type is equal on both sides of the equation. Here are some lecture problems I'm going to throw at you to introduce you to this concept. The lecture problems read, balance the following equations, and then you're given two different equations. You might ask yourself, what types of reactions are these? You'll note that I've got two substances on the left combining to form one substance on the right. So this is indeed a combination reaction. In this particular reaction, I have two substances on the left and two substances on the right. What type of reaction is that? Well, that is a type of reaction that I will talk about in a later lecture. In any event, you don't need to know what type of reaction each of these are in order to balance them. I'll prove that to you by showing you how to balance these on the DotChem.
In this chemical reaction, we see that if we take carbon monoxide gas and treat it with oxygen gas, it makes CO2 gas. Here's what we do. We want to balance this equation. What we do is we start counting how many atoms on the left and the right side of the arrow. I'm looking at carbon atoms. How many carbon atoms do I have on the left side of the equation? I've got one carbon atom. On the right side of the equation, how many carbon atoms do I have? I also have one. So the carbon atoms are balanced. Now let's look at our oxygen atoms. How many oxygen atoms do I have on the left? I've got one here, and remember O2 is actually two oxygen atoms, so this little subscript 2 also tells me that I have to multiply that by 2. There are 3 total oxygen atoms on the left side of the equation. How many oxygens are there on the right side of the equation? There are only 2. So as you can see, oxygen is not balanced. What in the world can I do to balance it? What I'm going to do is I'm going to add coefficients. That is, I'm going to write numbers to the left of each item wherever I need to in order to ensure that I have the same number of all types of atoms on the left as I do on the right. Sometimes, if you get a lot of practice at this, you can see exactly what numbers you need to add and where. You might not be that well practiced yet at this. So sometimes you can kind of do it a little bit by trial and error just to begin until you get to the point where you can do it or see exactly where to go. So let's see if we can write a coefficient in front of something somewhere. Someone yell out a coefficient. There's no right or wrong answer at this moment in time. And just tell me a number. It has to be a whole number, 1 through infinity. Tell me where to put it. All right. So we're told to put a 2 in front of the CO. All right. So let's go ahead and put a 2 in front of the CO. If I do that, how many carbon atoms total do I have on the left side of the equation? I've got 2. How about on the right side of the equation? I still have 1. So how can I balance the right side of the equation with respect to carbon? I can put a 2 right here. So let's take a look and see if that helped things out. So my carbon on the left side of the equation now has 2, and my carbon on the right side of the equation now has 2. Let's now count our oxygens. Remember that if I put a coefficient to the left, it's multiplied all the way through, which means that there are 2 oxygen atoms here now. So I have 2 oxygen atoms in this from this compound, and I have 2 oxygen atoms from our O2 still. So how many total oxygen atoms do I have? Yeah, I've got 2 plus 2 equals 4. And that's about as intense as the math gets. How about on the right side of the equation? This is kind of tricky. I've got a 2 multiplying through, but there were already 2 oxygens here, so the total number of oxygens actually gets multiplied. 2 times 2. The total number of oxygens then becomes 4. Is my equation balanced? Yes, it is. That's how you balance the equation. This is called stoichiometry. The process of balancing equations is called stoichiometry. It might seem a little silly. Why in the world would I waste my time doing this? The reason is because if I happen to work at a chemical plant where I've been asked to make carbon dioxide, and I want to make it from carbon monoxide and oxygen gas, I need to know how much of the ingredients to add into the reaction chamber. The stoichiometry tells me, actually, I need to add the reagents in a 2-to-1 ratio, carbon monoxide to oxygen, in order to get out CO2. Does that make sense? The stoichiometry is extremely crucial when we're setting up reactions that we use on industrial scale to actually make things, because it tells me in my recipe exactly what ratios of reactants to add.
Here are some more examples. Balance the following equations. And here are some more. Balance the following equations and indicate whether they are combination, decomposition, or combustion reactions. Once again, I will show you how to do some, but not all, of these on the DocChem. I'll let you tackle the rest of them, as well as the related problems on the subject in your problem set on your own.
Okay, so first things first. Once again, I like to start left to right, so I look at my nitrogen, and I ask myself, how many total nitrogens are on the left side of the equation? Well, there's one here, and there's one there, so there's actually two. Over here to the right, there are 2 nitrogens, so my nitrogen looks good and balanced. Not too bad. Alright, let's count hydrogens now. I have 4 hydrogens total on the left side of the equation. On the right side of the equation, there are 2 hydrogens. Not balanced. NH4NO3, N2 plus O2 plus 2 H2O. Alright, let's see if that makes sense. I've got 2 nitrogens still on the left, one here and one there. My nitrogens on the right are still 2. My hydrogens on the left side of the equation are 4, and on the right, remember once again that this 2 gets multiplied by this 2. There are indeed 4 hydrogens on the right, so that worked. Let's go to our next element. So we've got our nitrogens and our hydrogens balanced completely on both sides of the equation. Let's look at our oxygens here. My oxygens on the left, I've got 3 oxygen atoms. And on the right, I have 2, and then this 2 gets multiplied all the way through. So indeed, you are correct. I have 4. How in the world can I fix that? I think what we're going to do is we're going to add a 2 in front of this. Sometimes if we have odd numbers on one side, if we add a 2 as a coefficient, it will turn it into an even number, obviously. And that can occasionally fix things or make it easier for me to add a coefficient on the other side to balance it out. If I add a 2 in front of this, now the number of nitrogens that I have is 1, 2, 3, 4. So the 2 multiplies all the way through. I've got 4 nitrogens. Now, over here, I still have 2 nitrogens. Is there a way I can fix that? Now I have 4 nitrogens. My nitrogens are balanced. Hydrogen atoms, I've got 1, 2, 3, 4 times 2 is 8. 8 hydrogen atoms. On the right-hand side, I've got 1, 2, 3, 4. Is there any way I can fix that? Change the 2 to 4. So if I change that to a 4, now I have 8 hydrogen atoms. Now let's take a look at our oxygen and see what we've got. This 3 is multiplied by this 2. The 2 goes all the way through. So my total number of oxygens on the left is 6. Now on the right, I've got 1, 2, 3, 4 oxygens, 5, 6. Wow, holy smoke, that actually worked. Let me zoom in so you guys can see that a little bit better. I didn't expect that to work so darn easy, but it totally did.
We now turn to a different subject, Avogadro's number. What in the world is a mole? Well, we chemists often use this thing called a mole to measure stuff. Now, what is a mole? Well, strictly defined, a mole, also called Avogadro's number, which also happens to be the name of a band I once saw on iTunes, is 6.022 times 10 to the 23rd. It's kind of like a dozen, except instead of being 12, it's 6.022 times 10 to the 23rd, which, by the way, is a huge number. So why in the world would we chemists even care about such a bizarre number? Well, oddly enough, as it turns out, a mole happens to be the exact number of atoms present in a sample that weighs that element's atomic weight. Okay, let me do an example. I want you to look at your periodic table. What is carbon's atomic weight? Well, it's 12.011, of course. So what that means is that if you had 12.011 grams of carbon in your hand, you would be holding 6.022 times 10 to the 23rd carbon atoms. Alright, let's do another. The atomic weight of magnesium is 24.305. Now, this means that if you had 24.305 grams of magnesium in your hand, you would be holding 6.022 times 10 to the 23rd magnesium atoms. Okay, let's do one more. Let's look at xenon. Its atomic weight is 131.29. So, if you had 131.29 grams of xenon in your hand, you would have, you guessed it, 6.022 times 10 to the 23rd xenon atoms in your hand. I hope that makes sense. If so, let's go on to a great lecture problem. What is the mass in grams of a mole of carbon-12? Now, I have to answer this question by first explaining. You remember me talking in the previous slide about how carbon's atomic weight is 12.011 grams? Well, keep in mind, as we talked about in our previous chapter, that that number that you see on the periodic table is a weighted average that takes into account all three isotopes of carbon. Carbon-12, carbon-13, and carbon-14, and calculates a weighted average of all carbon atoms in the universe of weighing about 12.011. Here's something tricky though. This particular question is not asking you about carbon in general. If it asks the question about carbon in general, then it's talking about carbon-12s, 13s, and 14s in their relative percentages that they're found in the universe. This is talking about specifically carbon-12 atoms. So in other words, if you had 1 mole of only carbon-12s, no 13s, no 14s, what would its mass in grams be? You guessed it, it would be exactly 12. I hope that distinction makes sense. Here's another lecture problem. How many atoms are present in a mole of carbon-12? I hope you guessed it. 6.022 times 10 to the 23rd. Does that make sense? Cool. Now what about molecules like NaCl? Do they have atomic weights? Well, the answer is technically no. When we talk about the weight of a molecule, which is something that's made up of 2 or more atoms that are bonded together, we're no longer talking about an atomic weight. We're now talking about a molecular weight. It's mainly just a vocabulary difference. Atomic weight refers to the weights of individual atoms, and molecular weights refer to the weights of molecules. Molecular weights are also sometimes called formula weights or molar masses. So what in the world is the molecular weight of sodium chloride? We can determine this by looking at the periodic table. So as we look at a simple periodic table, you will note that sodium's atomic weight is 22.990. You'll also note that chlorine's atomic weight is 35.453. So what in the world is the molecular weight of sodium chloride? Well, each molecule of sodium chloride is comprised of 1 sodium and 1 chlorine combined. So the molecular weight of sodium chloride is going to be 22.99 plus 35.453, which equals 58.443 grams. Which brings us to some great lecture problems. Determine the formula weights of each of the following compounds: magnesium hydroxide, the active ingredient in milk of magnesia, and isopentyl acetate, responsible for the smell of bananas. I'm going to show you how to do these on the dot cam.
What I've done is I've written out the formula, so it's Mg with OH2 around it. So what I have to do is figure out the individual atomic weights of each of these elements and then add them together appropriately. What is the atomic weight of magnesium? Okay, 24 point what, Aaron? 0.3. Okay, oxygen's atomic weight is what? It's around 16. So I'm going to go 2 times 16, because there are 2 oxygens in each of these molecule of this compound. Hydrogen's atomic weight is around 1. So what I have to do is add 24.3. 2 times 16 is 32, and 2 times 1 is 2. I add all of these together, and I get the final answer. That is the molecular weight or formula weight of magnesium hydroxide.
Now, one thing that I want you to remember is this fact. Remember that atomic and molecular weights units are grams per mole. I beg you to remember those units. Grams per mole. What that means, once again, is that if I have 1 mole of said molecule or atom, it will equal that many grams. We now turn to a different subject, that of percent compositions. We chemists sometimes have to calculate a compound's percent composition, which is the percentage by mass of each element in the compound. Here's the formula, or the way of doing that. The percent composition of an element in a particular molecule is equal to the number of atoms in that element multiplied by the atomic weight of that element, all divided by the formula weight of the entire substance, times by 100. This brings us to another great lecture problem. Calculate the percent composition by mass of carbon in each of the following compounds. Cocaine, which has this formula, and vancomycin. I'll show you how to address these by looking at the DocCam.
So this is problem set 3, number 4, part A. So cocaine has the formula C17H21NO4. I'm not obsessed with illegal narcotics. I just think occasionally it's nice to grab someone's attention with a reference to one, like cocaine. The question is, what is the percent carbon? When I ask the percent composition of carbon, what I'm asking is how much of the molecular weight, what percent of molecular weight is made up of carbon. So first thing we have to do is calculate the molecular weight. So I've got H21, sorry. I got really excited with that one. NO4. So our formula weight, or molecular weight, is 17 times 12, 21 times 1, 1 times 14, and 4 times 16. 17 times 12 is, I have no idea, 204. Okay, 204. And 4 times 16 is 64. Yep, that's right, 64. So if I add all those together, I get the molecular weight of cocaine, which is M3. So it's 303, is that correct? So the formula weight of cocaine is 303 grams per mole. Let's go on to our next piece of paper. I'm asking you, what is the percent carbon? The percent carbon is simply the number of grams per mole of carbon in it divided by the number of grams per mole of the entire thing. So in other words, the percent, or the atomic weight of carbon contributing to that divided by the total weight times by 100. 67.32%. Number of significant figures, well, yeah. I've kind of thrown significant figures under the bus for these problems. Sorry, I'm trying to keep them very simple by using just whole numbers. But if we wanted to be a real super significant figure uptight, we'd actually use the full atomic weights with the decimal points on the periodic table on each of these. And then our final value would have the same number of significant figures as the component that has the least number of significant figures. That is the percent carbon.
We now turn to a different subject, using moles and formula weights and doing actual calculations. We'll do this by looking at a lecture problem. Calculate the following quantities: the mass in grams of 0.105 moles of sucrose with this formula, the moles of zinc nitrate, 143.5 grams of the substance, the number of molecules in 1 times 10 to the negative 6 moles of ethanol, and the number of nitrogen atoms in 0.41 moles of NH3. I'll go ahead and show you how to do some of these by looking at the DocCam.
For problem A, I'm asking, what is the mass in grams of 0.105 moles of sucrose? Sucrose's formula is C12H22O11. Here's the way we do that kind of problem. We first of all have to calculate what the molecular weight is. So calculate the molecular weight. So I've got C12H22O11. This is 12 times 12. This is 22 times 1. And this is 11 times 16. 12 times 12 is 144. I still remember my times tables from third grade. 22 times 1 is 22. And 11 times 16, I have no clue. 176. Thank you. If I add all of these together, I get 342. Remember that the units on a formula weight are grams per mole. And this is the reason why I keep reiterating that fact. If you remember that these are the units, it will help you figure out how to do the conversion much more quickly and easily. This is just old-fashioned dimensional analysis. And by old-fashioned, I mean something you learned like a week and a half ago. So I've got 0.105 moles, and I've got grams per mole. 342 grams in 1 mole. The moles cancel each other out. I times that through, and that tells me how many grams of sucrose I have. So 35.91 grams of sucrose. I want to do problem set 3, number 7, part C. In part C, I don't ask for moles. I ask number of molecules in 1 times 10 to the negative 6th moles of CH3CH2OH. Wow, that looks like a crazy hairy problem. Here's how we're actually going to do it. Once again, I'm going to put moles in the basement. I want molecules. Is there a way to relate moles to molecules? Yeah, okay. So can I write molecules on the top? What numbers can I put in there? All right, so I will write 6.022 times 10 to the 23rd on top, and on the bottom I'll write 1. Now I'm going to back off, and I'm going to say, or ask myself, is that a true statement? If I have 1 mole of something, are there indeed 6.022 times 10 to the 23rd molecules of it? There are. So this, Avogadro's number, is the way you can convert moles into molecules. So that tells me, if I times that through, how many molecules I have. 1 times 6.022 is going to be 6.022, and since I'm multiplying coefficients, I add them. 23 plus a negative 6, the same thing as 23 minus 6, times 10 to the 17th molecule.
Here's another lecture problem. The molecular formula of aspartame, which is also known as NutraSweet, is this. What is the molar mass of aspartame? How many moles are present in 1 mg? How many molecules of aspartame are present in 1 mg? And how many hydrogen atoms are present in 1 mg? And we end with one last problem. At least 25 micrograms of tetrahydrocannabinol, THC, the active ingredient in marijuana, is required to induce toxication. The molecular formula of THC is C21H30O2. How many moles of THC does 25 micrograms represent? How many molecules? I confess that in reviewing this lecture slide set, I think I might have had too many questions involving illegal narcotics. Hopefully I don't get investigated by legal authorities. With that said, I think it's a wonderful place for us to stop. I hope that you've had a wonderful time and that you stay tuned for our next and concluding lecture on Chapter 3's coverage of stoichiometry and calculations with formulas and equations. Until then, have a wonderful day.